All right, section 9.8 is on power series. We've been talking a little bit in class about this, the idea that when we build these Maclaurin or Taylor polynomials for functions, we're getting these polynomials that do a really good job of approximating values for e to the x or sine x or cosine x or natural log or whatever function it is that we're dealing with. This here would be an nth degree Maclaurin polynomial for e to the x. It goes all the way out to here and it stops. So because it stops, we can't say that e to the x is this thing. What we can say is that e to the x is about this thing. And so this is why we call this an approximating polynomial. If, though, we were to continue, so instead of stopping there, if we were to continue all the way past that term forever and ever, in other words, to do the infinite sum of those terms, then we can say that e to the x is exactly that. And so that's a difference. We're now no longer saying this is approximately it. We're saying that this is exactly what e to the x is. So in this crazy idea, e to the x, this irrational number that if we take it to an exponent of x, can actually be found by using just a simple little polynomial here. All right? Again, we've showed that, we've worked that out, we've developed that. But the question is, because of our last section, well, does that work for all x values? In other words, can I put anything I want in for x and have this converge to e to that power? And so when we deal with power series, we have to look at something called an interval of convergence, which we're going to get to in a second. So every power series can be viewed as a function of x. So we have f of x equals this power series here. For the one that we just talked about, our f of x was e to the x. Right? So that's the function we were dealing with, and it gave us this power series here. All right. So when we have a function, it can work this way. C would be the center of that power series. For our power series up here, our center was 0. All right? But we don't have to do 0 for other things. We might want to use something else as our center, but this would indicate what our center is at. The domain of this function is the set of all x values, which makes this converge. So in other words, what are values that I can put in here that would make this series converge, and what are values that I can't? And if there's something that I can't do, then that's not something I can put into my function. We had an example of that a few days ago in class, and we're kind of come back to that here. So there are 3 options for our domain when we do this. It is possible that the series will only converge at its center, at one single point. When this happens, that's a pretty useless power series. It is true, but it doesn't really do a whole lot for us. And so in those cases, those power series are kind of meaningless. Or a series could converge for all x values in the entire number line. This is very useful, right? Because what we're saying is that I can put any value of x into that power series. It'll converge to the actual value. I don't have to worry about will it work or won't it work. But sometimes we'll get a power series where it only converges for a certain interval. So it might be from, -1 to 3. And maybe it works at 3, but it doesn't work at -1. We'll talk about how that might be. Or we might have something like, from -10 to 8. All right? And it works at one, but not the other, or maybe it works at both of them. All right? There's no guarantee. We'll have to look at that, explore that a little bit more. All right? Now, in this first case, from -1 to 3, that would be centered at x equal 1. Right? And for this one would be centered at x equal -1. So we can see whatever the center, whatever the middle of this interval is, that's where the center of our power series is. And then the distance from the center to one of these endpoints. So for the first one, that distance was 2. For this one, that distance is 9. That's what we call the radius of convergence. Okay? So this interval here would have a radius of 2 and a center of 1. This one would have a radius of 9 and a center of -1. Doesn't matter if it converges at the end or if it diverges at the end point. It's not going to affect these measures, which is important to kind of keep in mind. Okay. Now, to find out which of these options that we're talking about, we got to recognize what kind of series we're working with. And sometimes the ratio test is going to be something that bails us out. But let's see if we can just kind of recognize at first what's happening and then let the ratio test kind of confirm that for us. So converges at a center only. So look at this one here. We've got n factorial, which is going to be something very big, times x plus 3 to the n, which is also probably going to be something big. Even if we put a number in for x that would make this value less than 1, like say you put in negative 2.5, which would create a 1/2 here. So we'd have 1/2 to the n. That's a geometric series that would keep getting smaller and smaller if it wasn't going against n factorial, right? The n factorial is going to dominate that. So we feel like this will diverge, except, so this is going to diverge everywhere except at x equal, and then you look, and the only thing that could possibly take out this factorial would be if this was 0. So if we were to put x equal negative 3 in here, that would create 0, and 0 times itself is still 0, and 0 times that is still 0, and that 0 will 0 all of this out. In other words, f of negative 3 is 0, because all of our terms would be 0, right? So at negative 3, this series converges to a value of 0, because those are the terms. But that is the only, that's the only value for this function. All right? That's the only function value that exists. And that's why I'm saying like this is a pretty meaningless power series. This is true, but then that's all you can really say about it. Now, if we were to do a ratio test on it, and I were to say, let's take the next term, the n plus 1, over the previous term. And we're going to take this, and we're going to take the limit as n goes to infinity. Now, normally, what we would do is we would say, is this bigger than 1 or is this less than 1? But this time we're going to do something a little different. We actually want to know, when does this function converge? In other words, we want to know what makes this less than 1. We want that to converge. And so the question now is not, does it converge or diverge? The question is, what values of x would make this true? Okay, so we're using the ratio test, but slightly different idea. We're not trying to say, does this go one way or the other, but how can I make this go less than 1? So if I do some simplifying, we get the limit as n approaches infinity of n plus 1 times x plus 3. And I want that to be less than 1. Well, n is heading to infinity. So the only way that this could be true is if x equaled negative 3. And so there's our kind of confirmation of what we had thought before. That's the only value that could make this true. If you put anything else in for x, the infinity here is going to drive that bigger than 1, and so then it would not work. All right, now when we look at this one, and we have the opposite thing going on. This is e to the x's power series, and we see that we have n factorial on the bottom. So no matter what we put in here, no matter how big that x is, that exponential will not defeat this factorial, right? And so we would say that this converges everywhere. Right? This is going to converge. No matter what you put in for x, this will work out. So in a sense, if you said, what is your interval of convergence for this? We would say that interval of convergence is negative infinity to infinity. It's the entire spectrum of numbers. And if we wanted to do a ratio test to prove that, all right, we'd have n plus 1 factorial divided by x to the n over n factorial. And we're taking the limit as n goes to infinity, and we want that to be less than 1. So this would be the limit as n goes to infinity of, and then if you flip and simplify, you're going to have x over n plus 1. Okay, so the question is, what finite values of x, when you let n go to infinity, make this less than 1? Well, they all do. So we get all real numbers for this, because any just plain number that you put in for x compared to something that's going to infinity will drive down to 0 and be less than 1. So this is a very useful, this power series for e to the x is really nice because it works for all x values. We don't have to worry about anything. But then we get something like this, and here's a power series that could definitely be something for us. And in terms of a series, this is x minus 2 to the nth power. That means what you're multiplying by over and over and over again is x minus 2. If you were to put 0 in, like if you say, well, what does this actually look like? This would be 3 times 1, so 3, plus, then we would multiply 3 by x minus 2, then we would multiply that by x minus 2 again, and then by x minus 2 again, and we would do that forever and ever and ever. That's what that series actually looks like. That's what f of x is, right? X minus 2 is the common ratio. And so this is fine. This is exactly what it would be, except that will only be true if the common ratio is between -1 and 1. So since we know that our common ratio is x minus 2, that's what we're multiplying by over and over again, then what we can say is that that ratio has to be between -1 and 1. And if we add 2 and add 2, then we get an interval of convergence of x between 1 and 3, which kind of makes sense. If I put anything bigger than 1 in, so say 1.2, I get -0.8. That's going to make things smaller and smaller. If I put in 2.4, I get 0.4. That's smaller than 1. Makes things smaller and smaller. If I were to put something less than 1 in, say if you put 0 in, you get -2 to the n. That's going to make things bigger and bigger and bigger. Put in 5, that's 3 to the n. That makes things bigger and bigger and bigger. This is the only thing that will work. And if you put 1 in or put 3 in, you're going to get -1 to the n or 1 to the n. That's going to create diverging series. Neither one of those works. So this is our interval of convergence. Okay. And we would say that we have a radius of convergence equal to 1. Our center is at 2. And from 2 to either endpoint is a distance of 1, okay? That's how we would say it. Now, if you did a ratio test on this, that would not be wrong. In fact, it'll just confirm what we said here. And sometimes they'll ask you to make a ratio test and show this. So here's our setup. The limit as n goes to infinity of the next term over the previous term, and we want that to be less than 1. If we do a little simplifying here, the 3's cancel, and that goes down to just x minus 2 less than 1. Now, one thing to notice and be smart about is it doesn't actually matter anymore what n is going to. There is no more n's here, right? So this kind of fades away. We don't need to worry about that. We're really just interested in when is the absolute value of x minus 2 less than 1. And so in order to have an absolute value less than 1, it would have to be between 1 and -1, which is going to then give us the exact same thing we had before. So it's just same answer, just from a different way of getting there. Sometimes it's as simple as this when you see that common ratio, but if you don't see the common ratio or there's more going on, then we'll need to set up a ratio test to get there. So for example, if we see this one here, all right, we've got a lot of things to the n power. And so maybe in a case like this, a ratio test would be something that we'd want to go to, the limit as n goes to infinity of the absolute value. And because we're doing absolute value, the alternator is going to not matter. Right? If you put -1 in there, it will come to a -1, but the absolute value is going to get rid of it. So we don't need to worry about the alternator when we do that ratio test. We just have to worry about the next term of this. So the next term from n minus 1 would be n over 5 to the n plus 1 over x plus 3 to the n minus 1 over 5 to the n, and we want that to be less than 1. So if we do some simplifying, what we're going to get is x plus 3 on the top, 5 on the bottom. There's no more n involved, and so we don't need to worry about that limit anymore. Okay, it just doesn't apply in this case here. Again, the only way that an absolute value can be less than 1 is if it's between -1 and 1. If we multiply by 5 and then subtract 3, we get x between -8 and 2. That's our interval of convergence. So interval of convergence is -8 to 2. That's centered at -3, which we could have predicted from the beginning, but then from -3 out to either endpoint, the radius of convergence would be equal to 5, a distance of 5 from -3 to here or from -3 to there. All right. Now, that again is using the ratio test to kind of get there. If you had said, well, look, I know that this is to the n power, this is to the n power, so it's really my common ratio is x plus 3 over 5. And even if you had put the negative in there, it would not have mattered, because then you would have put that between -1 and 1, multiplied by 5. If you would have done the negative, that's okay. It would have just flipped everything around like this. And then when you subtract 3, you still would have gotten the same answer. 8x is between -8 and 2. It just would have been flipped over with that. So that's where the negative is fine if you included it, but won't necessarily matter. Okay? Now, if we do the ratio test, and it gives us an interval of convergence, oftentimes we must test the endpoints of it to acquire the full picture. Okay. Now for our examples here, for like this one, if you put -8 in for x, what you're going to get, and I'll just do it right over here. Okay, when x equals -8, and we put that in for x, we're going to get the infinite series -1 to the n. We're going to get -5 to the n minus 1 over 5 to the n. And this can get a little complicated for sure. But let's kind of focus here. If we take a 5 out of this and a -1 out of that, what we would have is a -1/5, just kind of an extra -1, an extra 5 just over here. And then everything else would be to the n minus 1 power. And so then we could multiply it all together. You would have -1 times -5 divided by 5. That would give us a 1 to the n minus 1. Well, 1 to any power is still 1, so that's just going to be -1/5 over and over and over again. This diverges. Okay, so we know that the -8 didn't work. If we put 2 in, we get -1 to the n, we'll get 5 to the n minus 1 over 5 to the n. And again, if we take that little extra -1/5 out and then multiply everything together, we're going to get a -1 this time to the n minus 1. So what this does is it's going to go 1/5 negative plus -1/5 plus 1/5 plus -1/5. That's still going to diverge. Okay. So both of these endpoints diverge. This is what they're talking about. Like, you have to kind of test those endpoints when you do it. And you might wonder, well, why the heck do I have to test them? It looks like they're going to diverge every time. Well, when you start throwing extra junk in with it, that's not the case. So like if you looked at this and said, well, x is my common ratio. My common ratio is just plain x. So I need x to be between 1 and -1, and there's my interval. You're going to be partly right. But let me show you through the ratio test. We'll get to the same place, but then we're going to show why that's not the full answer. So we'll have x to the n plus 1 over n plus 1 divided by x to the n over n. The limit as n goes to infinity, and we want that to be less than 1. So that gives us the limit as n goes to infinity of x over n plus 1. I'm sorry. x, yeah, maybe a better way of writing that. It'll be n over n plus 1 times x. Okay? And now, because we're taking n to infinity, n over n plus 1 is going to go to 1. And so we'll get the absolute value of x less than 1, which gives us the exact same thing. And you're wondering, well, what the heck? Why did we have to do all of that? Well, we technically probably didn't. We probably could have started at the same spot. But here's the difference. Now we want to test those endpoints, okay? We're going to test -1 and we're going to test +1, okay? So let's start with -1. If we put -1 in for x, we're going to get -1 to the n over n. Okay, now that is an alternating series on a sequence that goes to 0. This converges. And so what that means is that -1 technically works. And when I do my interval of convergence, I have to include -1 because it technically worked. But if I put 1 in, I'm going to get 1 to the n over n, which is just the harmonic series. That's going to diverge. So I don't include 1. So here's a case where we got the initial interval from just knowing what the common ratio was or doing this, but then there was a little bit more to the story. And an AP grader is going to see, did you test your endpoints and did you get correct answers when you tested them? Sometimes it's easy and sometimes it's not as easy, but it is important for us to make those tests to see. All right. So let's look at another example. We have this one here, and we see that x minus 2 to the n is that common ratio. So x minus 2 has to be between -1 and 1, which means we're pretty sure that our initial interval is going to be from 1 to 3. Sometimes if it's multiple choice, it can be just that quick and simple. But if we're doing it, they might ask us to do the ratio test to show the interval convergence with all the endpoint stuff on it. Again, with the absolute value, we don't worry about the alternator. We're just going to put in x minus 2, next term would be n, over n plus 1 cubed, divided by x minus 2 to the n minus 1 over n cubed. And we want that to converge, so we want it to be less than 1. So we get the limit as n goes to infinity of n cubed over n plus 1 cubed times that extra x minus 2 that's left over. Now again, because n is going to infinity, this is going to go to 1, which means we will have x minus 2 less than 1. The only way the absolute value of x minus 2 is less than 1 is if x minus 2 is between -1 and 1, which gives us the exact same thing we thought we were going to have anyway, right? But sometimes, again, the graders will be looking for this. It's not enough to just simply say that. So no big deal. We give them what they want, but then we have to test those endpoints. Okay? So if I put 1 in for x, we're going to get -1 to the n. We'll get 1 minus 2, so another -1 to the n minus 1 over n cubed. Now, it's a couple different ways you can think about it, but if you ever get confused, I would say just put 1 in for n, 2 in for n, 3 in for n, and see what's happening up top. So if you're not really sure what's happening going on there, just put some numbers in and see. But I'm going to go ahead and combine these. So this is -1 to the n plus n minus 1. That's 2n minus 1 over n cubed. Now the curious thing happens, when I put 1 in, I get 1. When I put 2 in, I get 3. When I put 3 in, I get 5. Every time I put an n in, I'm getting an odd number, which means that this is going to be -1 over n cubed, and that diverges. That's not an alternating series. It's not -1 to the n, which would go positive, negative. This is always negative. It's just simply the -1 of that. Now, I said that diverges, but now I'm going to take that back. Because this is actually a p series, p bigger than 1, that converges. So we will include 1 with our answer, okay? And then we'll go ahead and test 3, and that's a negative 1 to the n. If I put 3 in, I get 1 to the n minus 1 over n cubed. That 1 to the n minus 1 will just go away. And now we have an alternating series on a sequence that goes to 0. For sure, this converges. Don't even have to worry about that. So we'll also include that. So that means our interval of convergence is 1 to 3. Centered at 2, we have a radius of convergence equal to 1. So let's kind of put this out to a bigger idea. So this says f of x is a power series. It's centered at 5. It has a radius of convergence of 3. All right, so if we kind of think of almost like a number line here. So centered at 5 has a radius of convergence of 3. So if you go 3 spaces out here to 8, or 3 spaces back here to 2. Now, those are the endpoints. We might include them, we might not, right? So it doesn't, whether it converges or diverges here is still not sure. But what we do know is it converges everywhere inside of this interval and it diverges everywhere outside of this interval. So first question is, does this converge at 7? 7 is inside of it, so we would say yes. We definitely converge at 7. Does this converge at 14? The answer would be no. Diverges at 14. It's outside that interval. Where can we say it converges for sure? We can say that this converges for sure between 2 and 8. About those, we're not sure. Maybe, maybe not. Okay. I give you this power series. It looks really complicated. I say, where's this power series centered at? You just simply look at here, see x minus 4. It's centered at 4. Okay. Just kind of some basic stuff to make sure we've got the handle on this. This one says a power series has an interval of convergence of this. Where is it centered? What's the radius? So again, the center is right in the middle. So we're centered at x equals 6. And we have a radius of 3. And just some basic thing there. All right, I think I'm going to jump to here now. And when you take the derivative of the power series or you integrate a power series, I get really cautious about how simple this looks, because I think sometimes it's easier to write out your terms. But you'll notice that we have this written in this nth power. And if you want to take the derivative of this power series, you notice how the n dropped down, and then we just subtracted 1 from there. Like that is, in a sense, sometimes just that simple. That's how you'll take that derivative. Or in this case here, we added 1 to the exponent, divide by the new exponent. Sometimes it is that simple, but I kind of think the easier way to handle it is to then just write out what I have. So for example, here it says, write the power series for this and state the interval of convergence. So if I took this here and I went, well, f of x is, put 1 in, I get x. Put 2 in, I get x squared over 2. Put 3 in, x cubed over 3, plus x to the 4 over 4, and dot, dot, dot. So I have the first little handle on that. So then my derivative would be 1 plus x squared plus x cubed plus dot, dot, dot. And then if I kind of say, well, let's see, that's 1, that's 2, that's 3. Looks like to me that this is going to be x to the n, right? From 0 to infinity. Now that is the same as x to the n minus 1, which we would have gotten if we just came up here and said drop the n, let them cancel. We have x to the n minus 1, and kept it for where it started, right? Like these are the same thing, And so it doesn't matter which one you use to write something like that out, that's what you'll get, okay? And then the same thing true here. If we have something a little more complicated, it says, is g increasing, decreasing, or neither at x equal -1? Can we write the first four terms of this? So what I like to do is just write the first four terms in general. If I put 0 in, I'm going to get x over 1 squared, so 1, plus put 1 in, we're going to get x cubed over 4, then x to the 5th over 9, x to the 7th over 16, dot, dot, dot. All right, so the first question is g increasing, decreasing, or neither at -1? Well, what I want to do is, let's go ahead and do the derivative. So g prime would be 1 plus 3x squared over 4 plus 5x to the 4th over 9 plus 7x to the 6th over 16 plus dot, 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 right? That's g prime, and we're asking about what's going on at -1. So if I put negative g prime -1 would be 1 plus 3 times -1 squared over 4. Well, that's 3/4. And then this is going to be 5/9, 7/16 plus dot, dot, dot. Well, that's going to be a positive value, right? There's no way that that could equal a negative. There's no way that could equal 0. And so since my derivative at -1 is positive, g is increasing. And then B says, can you write the first four terms, the general term for the integral of g of x? Well, again, if this is g of x up here, then the integral of g would be x squared over 2 plus x to the 4th over 16 plus x to the 6th over 54 plus x to the 8th over 128, I believe. All right, plus dot, dot, dot. Now those are the first four terms, that's right. But then to make a general term would be a little tricky. I know that we'd have, I don't need that for that, general. I know it's gonna be x to the 2n, that part's easy. But then when you look at 2 to 16 to 54 to 128, that's a little less obvious, right? And so what I'm gonna do is I'm gonna kind of re-split them. So this was 2 times 1, this was 4 times 4, this was 6 times 9, this was 8 times 16. That way it's 2n times n squared. And then if I want to go, oh, well, that's 2n cubed, okay, well, that's great, now I see it. But before it was a little bit tricky, right? Either way, again, this would be the simplified one, but I think either one of those works.